I'd like to talk about measuring microservices. And actually it was really cool. One of Adrian's slides I thought was really interesting was this question of how on earth do you manage deployment of microservices when you break stuff, and measuring the effects of the system and using that to know if you've broken something is actually a really powerful technique, which I'm going to go into so you can understand how you use it in a microservices context. So this is kind of a motivational example. So if you think about the human body, we don't measure the health of the human body by measuring the flow rates in ion channels on individual cells. You measure it by measuring emergent properties, things like blood pressure and heart rate. And in the same way, we can't really understand a microservices system by measuring the telemetry of CPU loads and things like that, individual services, especially not when you have 158, I think it was. That's really cool, by the way. You have to measure a larger set of properties. So, in the sort of the confessional spirit that Adrian opened with, Uniform started out doing Node.js. Node.js, if you've used it, is something that kind of pushes you in the direction of microservices anyway, because it encourages you to write really small little scripts. We've been doing microservices essentially for about 3 or 4 years before we knew what they were called. We built them in every possible configuration, from the REST-based ones that Guild is used to message queues, to other sort of weird and wonderful experiments. So we've made a whole bunch of different mistakes. This talk is, in one sense, an empirical report. So it's not a, here's how you do microservices, or here's how you measure them per se. It's more, these are the types of issues that we've encountered, and these are some of the approaches that we're taking, which seem to be relatively successful. But again, this is a process of discovery. So I'd like to kind of broaden the idea of what microservices are to begin with. And a lot of the talks that you see and a lot of the blogs that you see talk about them in a particular context where they are essentially web servers, where different, one microservice serves one page, for example. We see them as being slightly more general. So not only could a microservice serve an individual page, but there's a whole set of microservices beneath that that are doing all sorts of different things. And essentially, microservices are just, in that perspective, independent processes that exchange messages. Not necessarily over HTTP, it could be in any way. And it's this message exchange that's fundamental in our experience. And it is the behavior of those messages that has the emergent properties. And really the way this kind of manifests itself is by looking at message flow rates. So, and again, I'm just going to riff on some of the stuff that Adrian brought up, because he sort of anticipated one of the examples that I'm going to talk about. So, your guys did a deployment, was it last week, and they broke logging for 20 minutes?
Yeah.
Also examples. So,
sorry.
You can see how my examples are not actually made up. This happens in real life with these systems. Message flow rate is a powerful measure because it's independent of the services, in the sense that you have a certain number of users logging in per minute, let's say, which is going to generate a certain flow rate of login messages that flow through the system, and their dependent messages and so forth. That is independent of whether you have 4 services or 2 serving logging. The flow rate is a much more interesting measure. Let's say you do a deployment. So this is probably what happened to Guild a week ago. Right, so here's a chart showing logins per minute. And you can see there's a little downward trend to begin with. That's probably because it's heading into late afternoon and fewer people are using the system. And then a deployment is done and suddenly all hell breaks loose and the login rate starts falling dramatically. And that tells you that whatever update you've done, your updated login system has broken something in production. So this technique of measuring what is essentially an emergent property is extremely powerful. CPU load is not going to solve this problem. Unit testing, all your unit tests can pass and you can still have this issue. So what we've found is that by focusing on message flow rates, you can get this powerful measure. And because it's such a simple thing to do, it's something that actually gives you a really useful tool. And when people think about microservices and they think about the complexity of all these messages flowing between different services and how do you write a dashboard where you see 158 different services, if you actually decompose that down into looking at the flow rates of different message types, you get a much easier way to get a feel of whether your system is behaving or not. So that's all very well, but where do you start? What do you decide to measure? Well, actually, we can take a step back from the question of what to measure and think about microservice systems in general. Because what we've also seen in practice is that there are certain patterns that are emerging in these microservice architectures. And they're relatively obvious when you think about it. One is an actor pattern, where you have messages being generated by some service, and then you have a set of actors that act on the message. And it's round robin, right? So not everybody sees every message, each one acts on a new message in turn. This is kind of a classic message queue implementation. This is one relatively common pattern. Another one is a subscriber pattern, where actually every service sees every message. So sometimes you use this when a user logs in and you want to announce to the world that the user is logged in because different services want to act on that in different ways. Another common pattern that we see is this chain pattern. So this is actually one of easy ones to criticize. So for example, if you have an e-commerce site and you have to check out, there's a set of sequential processes that you have to go through. And if they're written as microservices, this is a sequence of messages that has to happen. And yes, it is high latency. But it's still a relatively common pattern that we see. And this list is by no means exhaustive. It's just giving you a flavor for some of the things that we see in production. Another really common one is a tree, where an initiating service generates a kind of a flowering of different messages between different services. Some of which may end up in feedback loops. And again, this is something that sometimes just emerges as the system gets built, and it's different development groups, in the spirit of anarchy, add different services that do different things. So, why are we doing this in the first place? Why are we actually deciding to use microservice architectures? I think you have to kind of step back and take a look at what monoliths have actually done for software development. So you have large enterprises who have things like December lockdowns for code. You have issues where Ulster Bank had an issue a year ago where they did a deployment and it screwed up their systems, and then people in all weekend fixing their accounts by hand. The whole point of this microservice architecture is to reduce risk, because if you can change individual pieces of the system and measure the effects of those changes, you're not doing a big bang all or nothing deployment. It's easy to unroll changes in the system and the risks they introduce. So it's about reducing the risk. It's not about eliminating the risk. Any software system, any software architecture is still going to have some measure of risk. But what's powerful about microservices is that it kind of cuts through the bullshit, because a lot of software approaches and a lot of software methodologies kind of promise 100% effectiveness. So if you're decide you're going to practice Scrum or Agile or any of these different methodologies, and yet your project is still late and over budget or doesn't have the right features, well, you didn't follow the process. It's your fault. Right? This is the issue. These things are ineffective. this microservice pattern actually gives us a grasp on reducing risk in a measurable way. So, for an idea of what that means, if you think about the ways that we try to reduce risk, these software methodologies, even things like unit testing or code reviews or coding standards, you have to ask the question, what do they actually buy? So in our guts, we know we should be doing unit testing because it does make us feel better at code and it makes refactoring easier. The whole question of whether you should be refactoring in the first place is another question. But the issue is, how many times have you been in a situation where you have hundreds of unit tests and they all pass and you go to production and something still breaks? In fact, we had exactly that situation. Exactly that situation. We had a code base with 600 unit tests, a sort of hybrid monolithic microservice-based system, went into production and still didn't work, even though 600 unit tests were passing. And you would think that 600 unit tests gives you some sort of measurable number on the risk that you've eliminated or reduced in the system. But in reality, these things are not particularly effective. What we need are actual scientific measures of risk reduction. And this is where microservices come in, because they allow you to do this. So we've started using, in the last 3 months, a couple of different techniques based on this idea. So we've taken the best practices, the unit testing and acceptance testing, all that sort of stuff, and put them in the middle and attack this problem from both ends. So on the front, you can actually use formal methods. And I'll talk about that in a minute, because that's actually quite effective. And then on the back end, you can use measurements. So this is when you're in production, you can measure the system, and you have a real measure of how things are doing. So, just returning to this login example, right? So you deploy, login breaks, but because you're measuring, you have a real measure. This is not a fake measure. This is not, we did 3 months of QA. We went through some wonderful process and things still broke. This is an actual measure of real production code. And I think one of the questions Adrian previously actually raised an important thing that you can do with this. It's not necessarily the case that you can just replace a microservice with a new version. You can run the new and the old versions side by side, and you can check this chart in production, but still have your system working, because the old version of microservice is handling the actual traffic. The new version is simply there to test against production. That's a really, really powerful technique. On the other side, you need to look at formal methods. So here's a question for you. Okay, are you planning to learn a new programming language this year? So who's planning to learn Go? And Go is not such a bad language. Who's planning to learn Swift, let's say? Any other languages? Haskell. Haskell, woo! So I would say this might be an interesting language to learn. This language is called TLA+. And it was invented by a guy called Leslie Lamport. Anybody heard of Leslie Lamport? So he is basically the guy who turned tech into LaTeX. He's the guy who invented the Paxos leadership election algorithm. He invented vector clocks. So he's basically like the king of distributed computing. But he basically looked at what people were doing with formal methods and found a way to make them practical and to give you a measure of risk. So if you studied formal methods or read about them, the whole idea is that you can prove that your software system is correct. The problem with that is it's basically impossible to prove anything but a trivial system. But what Leslie Lamport did was take that idea and combine it with the way that chess-playing programs work. So a chess computer doesn't prove that it's going to win. It explores the state space of moves down to a certain level, so that it has a high confidence that the moves that it's going to make will allow it to win. It has some sort of heuristics and some sort of measure that the next move is a good one. And that's what this approach, this TLA plus, allows you to do. It allows you to define your system and then execute a mathematical model to explore that state space. So here's an example, right? This code here. This is a formal description of a 12-hour clock. So even though it's written in kind of mathematical terminology, if you look closely, you can still follow it. It works in a very, very simple way. There's only two things to understand. The initial state of the system. You have the variable HR, and it can only have values from 1 to 12. Because it's a 12-hour clock. There's no 0 hour, there's no 13 hour. It only has values from 1 to 12. And then you ask yourself, how can the system change? Well, if the hour is 1, it increments to 2. If the hour is 2, it increments to 3, and so on. And if the hour is 12, it goes back to 1. And you can see the two lines of code, HC ini and HC next, cover those possibilities. The initial state of the system and the valid states that it can move to. And if you simulate this, you can explore these set of states. And obviously, this is a really, really simple system, right? You can explore all the states. There's only 12. And you can be sure that it's not going to go wrong. And when I say go wrong, I mean something very, very specific. I mean something called, the technical term for them is invariance. And the invariant in this system is that the variable HR can never be outside 1 to 12. And what that formal method has done is allowed us to detect this invariant. It's allowed us to specify a belief about the system. So, how is this useful? Do you actually need to learn TLA+? I would recommend it. It's really, really cool. By the way, this is a software specification that has no boxes and arrows. That means it's a good specification. It means it's a real one. Invariance lets you do the following. So let's take our e-commerce application. And it's a microservice system. So whenever I add an item to the shopping cart, I want to recalculate the sales tax. So naturally, I have an add item message, and I might have a sales tax message, and I might have a cart microservice, and I might have a sales tax microservice. Works out the details of sales tax. And I know that the invariant in my system is that when I have an add item message, I also have a sales tax message. The count of the messages should be the same. But of course, because of network latency and all sorts of other things, they aren't going to match exactly. And if you trace the number of add item messages and the number of sales tax messages, they're sort of going to correlate. But then you have trends. You can see there's a slight upward trend here as, I don't know, we move towards lunchtime and people are shopping online. But there's an invariant, which is the ratio of the two messages, which should be 1, whether it's midnight or lunchtime or whenever. The invariant is 1. And if that invariant changes, then we know we've broken something in our system. So you don't need to understand formal methods to actually do this, right? There's a practical way to start using these things. You can take the microservice patterns and you can just determine some simple invariants from them. For example, the actor model. Well, you know that 1 over n is the amount of messages that any microservice should see. That's an invariant. It doesn't matter how many messages there are, it doesn't matter how many actors there are. The invariant is easy to describe. The subscriber is pretty much the same, except this time it's n. The chain, it's the number of links in the chain. The tree, it's the number of leaf nodes, the number of final resting places for the message flows. And there are many other ways of constructing these types of invariants. But if you look at your message patterns, you can find invariants very, very easily. This philosophy is actually quite powerful because it's a way of looking at software that kind of inverts the normal way we, as software developers, think about things. And there's a really nice quote from a guy called Chris Newcomb in AWS, which is, "Ask not what can go wrong, ask what must go right." So you might be thinking, well, this is all very well, but still I don't see the practical application. Actually, Amazon uses this stuff. So if you use S3 or DynamoDB, the worst thing that can possibly happen is data destruction. Is Amazon somehow losing your data. That's the worst possible bug that they can have. They use this approach to model DynamoDB or S3, and they actually ran the simulation, the state space simulation, I think over a period of 3 weeks, right? So Amazon's got the compute power, it's not a problem for them. And I think it was at the 35th step of one particular execution trace that they found a data destruction bug in DynamoDB. So I'll put up these slides, and you can see there's a link there to the paper explaining this stuff. So this idea of using invariants to measure a production system and to detect errors actually works. And Amazon is using it really, really effectively. But again, you don't have to learn a formal methods language like TLA Plus to put it into practice. You can define invariants very, very simply. Because a lot of the time, they're kind of obvious. So if I have, for example, a login microservice that generates 2 other messages, well, I have this invariant, this ratio between an inbound login message and 2 other outbound messages, and the invariant shows me 2. And if I do a deployment, and the invariant changes to 1, I know that I've broken something. Finding these invariants is relatively simple. In fact, we can think of a couple of cases where you can pull them out quite easily. Simple one is the business rules around the system. So if you're upgrading payment processing part of your e-commerce application, invariants relating to the fact that successfully checking out means you have to send an email or you have to generate an invoice are pretty obvious. You also get a very powerful error checking facility around something called subcriticality. So in the North Sea oil platform industry, they have this thing called the rule of 3. Basically, there's all these different critical levels that things are at. So that's it, I'm done. Bye. yeah, you do one. So if your helicopter pilot has been flying, if he's flying for more than 10 hours, you can't fly, right? If the helicopter has been serviced in 3 weeks, you can't fly. If the wind speed is above such and such, you can't fly. But what they noticed over the years was that accidents were still happening. And they looked at a lot of the cases where the accidents happened, and they realized that all of these measures, these indicators, were subcritical. So they were within, let's say, 90%. But once you have these message flow measures, you can combine them in interesting ways, and you can detect subcriticality in your own system. And again, this is relatively easy to set up. You have different message flows that you expect to see in different invariants. And you can combine them mathematically so that if a subgroup of them becomes close to breaking, the meta invariant, let's say, also breaks. So, in summary, if you're building a microservice system, you've seen from Adrian's talk that it gives you all these wonderful benefits, but it also introduces a series of challenges. And one of them is around what happens when random developers can deploy to production and stuff can break. And how do you measure the system so that you know what's going on and can roll back and keep things within the safe parameters. Now, you can measure login rates directly, but the problem is the login rate will fluctuate during the day. Instead, you can think about your message flows, find invariants, and measure those. And that gives you a much more powerful and much more effective way to take control of the quality of the microservice system. And I'm going to take a few questions, but not that many because the pizzas are waiting. Thank you very much.
Have you tried mining that data and getting it meaningful out of it? Have you found any variants that you didn't know existed?
So we have been doing this intentionally for the last 3 months or so. I would say that we're essentially at the baby steps phase. That is definitely a thing that we want to do. And you can see actually, no, I'm just picking on you so much, Adrian. Adrian has already done some data mining. You can see from the analysis of lines of code and things like that, which is actually just encouraging me to start doing that in some of our projects. But yeah, that will certainly give you a feeling for some of the emergent invariants that you can't tell in advance. My feeling is that you can get really, really far with stuff that you can actually just see a priori, but when that does happen, I'm going to be really excited.
Yeah, just for a very just reminded me of code contracts. I don't know if you've ever heard that term. In your code, you have.
Oh yes. Yeah.
I'm just wondering if you could put that sort of measurement into your code, you know, as you're developing.
You certainly can. It tends to be this tends to be more probabilistic than exact, especially because of, again, things like network latency. So this is actually much closer to the idea of a production line that's producing widgets and they need to be 20 millimeters in length, and you're allowing a certain tolerance in nanometers. So it's much more that sort of thing than having an exact contract to say this variable is this type as an assertion. The interesting thing, if you get into TLA Plus and specifying formal methods, is that although it doesn't allow you to generate code, it actually gives you a nice way to determine what are the useful contracts to define. So when we use contract-based programming, it tends to be sort of arbitrary. And you're like, oh, well, these variables should definitely have these values, but it's sort of a bit scattershot. The nice thing about a formal specification is that it tends to drive you towards the important invariants. Again, I have to stress, I'm taking this formal method approach and this TLA plus as an inspiration. It's more of an inspiration to look for invariants in your message flows than it is a requirement to use microservices. Certainly not.
Do you have a more practical use case for this? Like you said, you're doing this in some of your production systems. What tools and technologies are you actually using today?
Okay, yes. So after trying out a whole bunch of different tools, we tend to use InfluxDB as the thing to capture the data. And the nice thing about that is it's a time series database. So it's very, very easy to actually monitor the data flows inside InfluxDB and then react to them. And I mean, this example of you deploy something and login breaks, and that's actually like a real example. And Peter, where is he? Oh, sorry. Peter is gone, unfortunately, but if you follow up with Peter, he's actually built some parts of this puzzle. And I think he's open source something as well. Okay, I'm not going to stand in front of your pizza any longer.